everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem, path with minimum effort, which is yet another problem in Dijkstra algorithm series. So in this problem we're given a, basically you are a hiker preparing for the upcoming hike. So you're given heights array. It's a 2D array of dimensions rows into columns, where each element in this heights array represents the height of the cell. Okay, you're situated in the top left cell, i.e. 0 0, and you hope to travel to the bottom right cell of the matrix, that is rows minus 1, columns minus 1. It's a 0 indexed matrix. You can move up, down, left or right. That means from any cell you can move to all of the adjacent 4 cells of the matrix. Now a route's effort is the maximum absolute difference in the heights between two consecutive cells of the route. Like for instance, starting from the cell 0 0, you take some route and you reach the bottom right cell of the matrix. Now along that route you find the effort as the maximum absolute difference in heights between any two consecutive cells of that route that you have taken. So we have to return the minimum effort required to travel from the top left cell of the to the bottom right cell of the matrix. Fine, so let's better understand the problem statement using an example. So let's take this example. Here you have this matrix. You have to start from the very first cell, that is from cell 0 0, which contains 1, that is the height of this cell is 1. You want to reach this cell 2 2, which has a height of 5, that is bottom right cell, and the path that you take is this one, that is move from the cell 0 0 to 0 1 to 1 0, then to 2 0, then to 2 1, and finally to 2 2. Okay, and we can see that the effort will be the maximum of the absolute height difference between any two consecutive cells of the given path. So here you can see that the maximum absolute difference is 2, because 3 minus 1 is 2, 5 minus 3 is 2, 5 minus 3 is 2, 5 minus 3 is 2. Now all of the adjacent cells has a difference of 2. So 2 is the maximum absolute difference and it is the effort of this route, and that is also the answer for this particular test case. Now this is what you have to find out. Okay, we have to find the minimum effort required to travel from the top left cell to the bottom right cell. So we have to minimize something. So you can see that we can use binary search to solve this problem, like return the minimum effort. We have to minimize the answer. The answer is the effort here. So that means find out the appropriate range of the effort. Effort is what would be the range of this effort. The left side, the left boundary and the right boundary, namely the search space, and just perform the binary search over this search space and find the first true element over that search space, that is the minimum effort required to travel from the top left cell to the bottom right cell. So if you don't know how to use binary search over a search space, please make sure to watch my binary search playlist, where I have taught the concept of binary search over the space. So if you are confused with the approach which I just explained here, then please go and watch that video, and after that you can solve this problem using binary search. But here in this video we won't be using binary search, rather we'll be using Dijkstra algorithm to solve this problem, because we are learning Dijkstra algorithm in this series. So let's see how we can use it. So Dijkstra algorithm is used to find the shortest path from one cell of the matrix to the other cell of the matrix. Here the source cell is this cell, that is cell 0 0, and the destination cell is this one, that is 2 2. Okay, now I want to find the shortest path thing here. Fine. So what is the parameter? What is the relaxation condition? So now all of these are variations of the Dijkstra algorithm. The tweak that we do in the Dijkstra algorithm is the is basically to change the condition for the relaxation. Like in this case, the relaxation will be performed on the basis of adjacent difference of the heights of the given path. So let's see how we can do that. So as usual, we take a priority queue, and in that priority queue, we're going to push the starting cell, which is 0 0, along with its cost. The cost is 0, or let's call it distance. So because it is a starting cell, we're starting from this cell. Then also take an array that is okay. So this is where we are given our effort array. So we have our effort array here. Now pop this node from the priority queue. Pop this only node from the priority queue, that is cell 0 0, and its distance is 0, or its effort is 0. Now traverse its adjacent cells, cell 0 1 and cell 1 0. Now here you can see that the effort to reach cell 0 1 would be updated by 1, because it is 2 minus 1, that is 1, and 1 is better than the effort that we already have for this cell, because we initialize this effort array with a very small number, which is 0, and we want to find the maximum effort to reach any cell of this matrix. Like to reach cell 0 1, I want to find the maximum effort along the route which I have taken to reach this cell 0 1, and that's why this matrix is initialized with 0. And now to reach cell 0 1, the maximum effort would be 2 minus 1, that is 1, and to reach cell 1 0, the maximum effort would be 3 minus 1, that is 2, because 2 is greater than 0. Now we also push these cells into the given priority queue. So push 0 1 along with its effort, that is 1, and push 1 0 along with its effort, that is 3. Now pop this cell out of the priority queue, that is this one, 0 1, this cell, and now from cell 0 1 traverse its adjacent cells, that is cell 0 2 and cell 1 1. So for cell 0 2, the effort would be the effort to reach cell 0 1 is 1, while the effort to reach cell 0 1 0 2 from cell 0 1 would be 0, because 2 minus 2 is 0. So we take max of these two efforts, we get 1 here. Okay. Now to reach cell 1 1, the effort would be for this transition 8 minus 2, that is 6. Is 6 better or greater than the effort for the parent cell? Yes, 6 is greater than 1 here. We have 1 here and 6 is greater than 1. So we will update this cell with 6, because we want to find the maximum effort that has been taken to reach a particular cell of. Okay, now let's push these cells into the priority queue. So push cell 0 2 along with the maximum effort, which is 1, and the cell 8 and the cell 1 1 1 1 along with its new effort, that is 6. So to arrive at cell 1 1, I require 6 units of effort if I move along the route, that is move from 0 0 then to 0 1, then from 0 1 to 1 1. Fine. Now out of these 3 cells which are there in the priority queue, pull this cell 0 2 from the priority queue, because it is nearest to the source cell. So from this cell 0 2, traverse its adjacent nodes, adjacent cells of this cell, that would be this cell only, that is 1 2. So to move to cell 1 1 2, we require an effort of 0 units, because the to make this transition from cell 0 2 to 1 2, we require 0 effort. So update the distance or the effort array for this cell, because the parent cell is this 0 2, and that we will update it with 1. Fine. So that means to arrive at cell 1 2 along this route from 0 0 to 0 1 to 0 2, then finally from 0 2 to 1 2, we require 1 unit of effort. Fine. Now pull this node from the priority queue, but before that push this node as well, that is 1 2 along with its effort, that is 1. Now pull this node from the priority queue, 1 2. Now from 1 2 move to its adjacent cells. The adjacent cells for this cell 1 2 would be this cell 1 1 and this cell 2 2. So traverse the cell 1 1. To move to cell 1 1, the cost required for this transition would be 8 minus 2, that is 6. Now check if 6 is better than the answer that we already have. We can see that we already have 6 here, so we're not gonna update it. Okay, so that's why we don't have to update the answer for the cell 1 1. So check for the cell 2 2. To move to cell 2 2, for this transition from cell 1 2 to 2 2, we require 3 units of effort, because the difference between the heights is 3. 5 minus 2 is 3. Now is 3 better than the answer that we already have? Since we have 0 here, 3 is better here. 3 is better because 3 is greater than the answer that we already have, which is 0. We want to find the maximum effort to reach at any cell. So what is the maximum effort? The maximum effort is basically the maximum difference between the heights of the consecutive cells along the route that we have taken. So along this route from 0 0 to 2 2, like moving from 0 0 to 0 1, then to 0 2, then to 1 2, finally to 2 2, we require 3 units of effort. Now push this cell into the priority queue, that is cell number 2 2, along with the newly updated cost or effort, which is 3. Now from these 3 cells which we have in the priority queue, pick this cell 1 0, and from this cell 1 0 we can move to cell 1 2 and to cell 2 0. Now move to cell 1 1 and check the effort that we so now move to cell 1 1, and the effort for this transition would be 8 minus 3, that is 5. That means to reach at cell 1 1, we require 5 units of cost. Fine. For this transition 1 1, for this transition from 1 1 to 1, from this transition from 1 0 to 1 1. Okay. Now associated with cell 1 0, the cost is 3 units. The cost is 3 units, and we can see that if I arrive at cell 1 1 along this route, that is moving from cell 1 0 to cell 1 1, I require 5 units of maximum effort, because 5 is greater than 3. 2 is the effort which I already have for this cell 1 0. It's not 3, it's 2 basically, it's mistaken. So we have 2 here. So we have 2 here, and 2 is the effort for the cell 1 0. And to reach cell 1 1, the effort is 5. Okay, the effort is 5. Now we can see that the effort that we already have here for the cell 1 1 is 6. But we are arriving at the same cell 1 1 through a better path, because this path, this new path in which we move from 0 0 to 1 0, then from 1 0 to 1 1, the effort is 5 units, which is better than this 6. So we update here the effort. So we update the effort with 5. Fine. And we push this cell again into the priority queue, that is cell number 1 1, along with its effort, which is 5. Also traverse this cell 2 0. Now to move to 2 0, I would require an effort of 5 minus 3, which is 2. Is 2 better is 2 greater than the effort which we already have for this cell 10. For cell 10 we have 2, and to move to cell 20 we have 2. So, okay, so we have to move from 00 to cell 20 along this path from 00 to 10, then eventually to 20. We require 2 units of maximum effort. Okay, and we update the array with this 2. Also push this cell into the priority queue. So push cell 20 along with its distance, that is 5, or that is 2. Now from these 4 cells, pull this cell out from the queue, that is cell number 20, and from this cell 20 we can move to cell number 21. So try to move to cell 21, and the effort that we require will be of 2 units. This transition takes 2 units, which is not better than the effort which we already have till cell 20. So we update here with 2 and push this cell 21 into the priority queue along with its effort, that is 2. Now pull again this cell from the priority queue 21. So from cell 21 I can move to cell 22, and the effort would be for this transition is 2. 5 minus 3 is 2. So is 2 better than the effort which we already have till this cell 21? No, we have 2 here, and this transition also requires 2. But this 2 is better than the distance or the effort which we already have for this cell 22, because previously we arrived at cell 22 along this route, moving from 00 like this here. But if I come to cell 22 along this route, that is moving from cell 00 to cell 10, then to 20, then from 20 to 21, and finally from 21 to 22, I require a cost of 2 units here. So I update this array with 2, and this is my best answer which I can have. And finally, and in this fashion I will prepare my matrix, and the answer to reach at the last cell, or the effort to arrive at the last cell for this test case, would be 2. Okay, simple Dijkstra algorithm. I hope you are getting how we arrived at the answer. Let's jump to the code implementation part, because it's just the Dijkstra algorithm with a little tweak in there. So let's write the code for this problems which we have explained here. So this is a minimum effort path function which takes in the heights matrix. So let's calculate the number of rows of this heights matrix. Calculate the number of columns of this heights matrix, height 0 dot size. Now declare a distance array. So a vector, a 2D vector called distance, initialize it with very large number M1E9, and initialize the very first or the source cell with 0, because we are starting from that cell. The maximum effort would be 0, and declare a priority queue and push this cell into the priority queue. Vector, vector of vector, push this cell into the priority queue. PQ dot push this cell 00 with its effort to be 0. Now also declare a directional vector to traverse the 4 directions of the given cell, the adjacent directions, -1 0 1 0, or not this one, 0 1 1 0 -1 0. Okay, so we cover all of the 4 directions. Now iterate till we have at least one element in the priority queue. Pop the top element from the priority queue. PQ dot top pop it from the priority queue and find the effort that we already have, the current effort that would be the first element in this top vector, the row number which will be the second element, and the column number which is the third element. Iterate over the adjacent directions, and for the current direction, that is xy, move to the new row or new x, that would be x plus dir I, new y, that would be y plus I plus 1, and then check if this new cell is a valid cell. New x is greater than equals to 0, new y is greater than equals to 0, new x is less than n, and new y is less than m. Now if it is the case, then update the effort. Find the new effort, max of effort that we have, and the absolute difference between the heights of the adjacent cells. So new x, new y minus heights x, y. Fine. And check if this new effort is better than the effort that we already have for this cell to reach the parent cell. If it is the case, not the parent cell, the current cell, new x, new y, then update the distance for this new cell. And push this cell along with the updated effort into the priority queue. New x, new y. Fine. And that's all. But here also use a early stopping condition. Also use a condition if the distance for the cell, for the current cell, is already better than the effort associated with this tuple, then continue to the next tuple. Otherwise, also check one more condition. If this cell that we have popped, n minus 1 is equal to x, if it is the bottom cell, m minus 1 is equal to y. In this case, return the effort associated with this tuple. Finally, if I never reach the destination cell, then return 0. So let's just try to submit the it worked, right? So let's try to submit it. Okay, it got accepted. So I hope you enjoyed the video and you learned something new, and it's another variation of Dijkstra algorithm over the grids. So that's all for this video, and in the next video we'll be discussing yet another problem of Dijkstra algorithm, and I hope to see you all in my next video.